Copyright University of Auckland, all rights reserved. The content and delivery of lectures in this course are protected by copyright. Material belonging to others may have been used in these lectures and copied by and solely for the educational purposes of the university under license. You may record the lectures for the purposes of private study or research, but you may not sell, alter, or further reproduce or distribute any part of these lectures to any other person. Failure to comply with the terms of this warning may expose you to legal action for copyright infringement by the copyright owner and/or disciplinary action by the university.
Does this sound okay? Can everyone hear me okay?
Yep.
Good, thank you. So yes, as Jennifer said, the Hochstetter lecturer is selected every year, and they are sent by the GSNZ on a national tour. So this year I'm giving this talk in 11 different centres across the country, and tonight is the 5th time I've given this talk. So hopefully it's the right amount of polish based on past experiences, but you've still got an enthusiastic speaker that I'm not too jaded and tired about talking about it. This talk is intended for non-geologists, so if you've come not knowing anything about Zealandia, never heard of it before, then you're right in on the entry level. That's good. I'm aware, though, that there are geologists in the audience. There are people that probably use Zealandia in their work, geological work as well, and I hope there'll be something in that for you as well. Let's get the lights down. Okay, how's that? So this is not exactly a talk outline, but it does mention some of the points and some of the strands that I'd like to get across to you tonight. Obviously, if we're talking about continents, we have to define what we're talking about. And depending on how you define a continent, you can come up with different numbers of them. So the first few slides of the talk will be devoted to how do we define a continent, in particular as geologists, how do we define a continent, how is that different from a geographic continent? And something else I want to emphasize is that we're neither me nor my research team nor GNS Science are claiming to have discovered Zealandia. Okay? This has been a very long process. The evidence has been building up for decades, for centuries even. But I think just in recent years, we've reached the point where we've got enough data and enough confidence in that data and the interpretations of it to make the case that we have got an 8th continent there on planet Earth. And the last few slides will be some fairly eclectic images about why this matters. Why does an 8th continent matter to science? Why does it matter to society? Now, at its most simple and its most cynical, this talk is all about turning an adjective into a noun. It's about turning the word continental into the word continent. For many decades, geologists have talked about New Zealand and its surrounding islands as being continental, but yeah, this is all about saying no, it's much more than that. It's a coherent whole that we can call a proper continent. So inevitably, it's about big picture geology and geophysics, and I think overall, calling Zealandia a continent gives a much more accurate and correct picture of what we've got down here in the Southwest Pacific. Now, something that all Hochstetter lectures are geared around is the publication of results. And Jennifer referred to a recent body of knowledge, and that body of knowledge is, I'm holding it in my hand here. It's a book called Zealandia, and this was written by my colleague Hamish Campbell. And here he is with our 2 Penguin editors at a meeting in Auckland. They've all got smiles on their faces because in November 2013 we just delivered the first draft. That's what's on the table there of the Zealandia book. Now, this talk is the Hochstetter lecture. I've not turned it into a book promotion tour, okay? Let me get that right. In fact, because you're here tonight, you don't have to read the book. You'll get all the highlights. So I've selected certain images from the book to show you tonight, certain illustrations. If you like maps and landscapes, you're in for a treat, okay? The book's actually divided into 5 chapters: identity, discovery, ancestry, life, and society. I've been selective tonight, just drawing on images and diagrams from identity, so we can define a continent, discovery, to explain how it's progressively, we've come to realize that it's there, And finally, society. So you're not going to get a blow-by-blow geological history of Zealandia from Cambrian to the Holocene, right? Mercifully. Okay, so let's start with three maps then. Three maps of the planet Earth. And these all explore different opinions as to what defines a continent. So if you go to the Oxford English Dictionary or any online dictionary and look up the definition of a continent, it's actually fairly concise, and they're all about the same. And they all talk about one of the world's large, continuous land masses. Okay, so those three words are all important. A continent's got to be large, it's got to be land, and it's got to be continuous. So what's important here is the shoreline, okay, so either the high tide mark or the low tide mark. Where can you actually walk that the land is continuous? So by that definition, there are two very large continents on planet Earth, labelled Old World and New World here, because you can actually walk from here, from Cape Town, over to Kamchatka there, without getting your feet wet, if you want to. So that's one continent, isn't it? And arguably, there are two other continents, or at least two very large islands, Australia and Antarctica, come into that. So, yeah, according to that simple definition, there should only be 2 or 4 continents. It's a bit unsatisfactory, of course, because that doesn't explain what we do with these large islands, Madagascar, Greenland, New Guinea, or New Zealand. And it's also unsatisfactory because it doesn't take into account the changing sea level. So climate change on all time scales, from centuries to millennia to millions of years to billions of years, sea level rises and falls. And that means that the sea level goes up and down the ramp, up and down the tide mark on continents. So some islands can become attached to the continents, and other continents could become separated if sea level rises, for example. So that's how a physical geographer might look at continents and define them. If we go to a human geography view, okay, what we're bringing in here are a couple of things. We've distinguished Europe from Asia. Well, of course, there's no physical geography basis, or even the geological basis, for separating Europe and Asia, but culture and politics and that sort of thing are so entrenched that, that's why Europe is considered a separate continent from Asia. In fact, this map here is probably the one that most people would readily associate with. Okay, the familiar 7 continents on planet Earth. Most people think there's 7 continents. But it's still, and we've also added some islands. So New Guinea is part of the Australia continent, Greenland part of North America. Those are fairly uncontroversial additions. But we've still got New Zealand in the grey there. We've not done anything with that. In fact, New Zealand, in the past has not been attached to any continent. Oceania and Australasia are not continents. They're geographic regions, but they're not continents. And we've still done nothing about sea level here, okay? So if we take the next slide is how a geologist would view the continents, and we come up with this picture here. So what we've done is added what are called the Continental Shelves to the map. So the actual continental area has expanded. We've got the planet Earth is 41% continental crust, not just 29% land. And you can see that some continents have very narrow continental shelves. Africa has got a pretty narrow, skinny one. Other ones are much wider. And you can see that this is quite clearly how places like Japan and Southeast Asia become part of the Eurasian continent here. And also for the first time, and you'll see this in many slides tonight, we've got this continent of Zealandia outlined, which has a really large continental shelf compared to the really tiny amount of landmass. So this definition is good because it's independent of sea level change. It takes into account the neighbouring islands as well. So it's a lot more robust. So if we look at let's just look at the geology, the solid earth underneath the oceans here for a minute. Okay, so most of planet Earth is water, and most of it's oceanic crust. In fact, the most common rock on the planet is a basalt. It's a very monotonous black basalt with a uniform chemistry called mid-ocean ridge basalt. The acronym is MORB. And arguably, this is the most common rock type on the solid surface of planet Earth. It underlies a lot of the oceans. So that's what oceanic crust, or the oceans, are underlain by mainly. Continents, it's pretty obvious when you're on a continent, okay? They're big objects. They tend to be high. Geologically, you have a variety of rocks. Here's some beautifully layered sandstones. Continents are also where we find a big diversity of rocks: granites, gabbros, gneisses, schists, greywackies, limestones, quartzites, far more diverse than those monotonous basalts that underlie the oceans. Now, if we take a cross-section through the outer layers of the Earth, and this is the depth in kilometres, you can see we've got a mountain range here that's underlain by a crustal route. You can see the continental crust, which is all these variety of rocks I've mentioned, tends to be quite thick. It's the geophysicists tell us this information from the seismic waves that travel through the Earth. They can identify where how thick this crust is. And oceanic crust is a lot thinner. Here's our sea level. And you can see this coast here, that's where the geographers define continents, whereas the geologists define continents here. So this continental shelf is that difference there. And so this is the edge of a geological continent. And we can understand and make sense of this continental crust. It does literally float on the mantle. It's got different physical and chemical properties. It's made up of light elements like silicon and aluminium, in contrast to the oceanic crust, which is very iron-rich. And those chemical differences lead to physical property differences, so density differences. The continental crust is more buoyant, it floats higher. Oceanic crust is more dense, it tends to sink lower. And they have different seismic velocities. So there's no formal definition of a geological continent, at least none that I'm aware of. There's no textbook provides a clear capsule definition, but all continents have these features of these 6 bullet points here. They tend to be high compared with the oceanic crust. They have that varied geology I talked about. The crust is thick. They're a large area. They still have to be large. They have to have limits. And for the most part, continents have old parts to them. They tend to be older parts of the planet. So what I'm going to do for the middle part of the talk, we're going to run down those bullet points and see how Zealandia stacks up against each of these criteria. Okay, can we put a tick by it for each of these features? So, yeah, this may seem like a remarkable thing to do. I mean, continents are arguably the largest objects on the surface of planet Earth. So how come one has stayed hidden for so long? Well, the early explorers, when they came to New Zealand, Aotearoa, they discovered some islands that were much larger than the islands in the Pacific that they were used to, but certainly it wasn't the size of a continent. As I'll point out later on, both Tasman and Cook were looking for the southern continent, but they both left New Zealand. Well, Cook circumnavigated New Zealand and satisfied himself that it wasn't big enough to be a continent. So with the technology that was available to Cook, he was right. Okay, there was no continent there. These days, we have much more technology at our fingertips, and we know differently. So we fast forward to the 1800s. I've collapsed the entire 19th century science into one slide here. This is the time of Hochstetter, when Hochstetter was in New Zealand in the late 1850s. And I'm going to show a sequence of 4 slides that show how our knowledge of the bathymetry of offshore New Zealand, the undersea plateaus and things, have gradually come into better and sharper focus. But back in the 1800s, in the Petermann Atlas, this is what we had. The islands of New Zealand, here's the Chathams, the subantarctic islands, and there's some hint of a shallow water around them. The shallow water around the islands just looks pretty token, but there is some hint, again, of maybe a connection to the southern continent down there. These are based just on a very few ship tracks of soundings of ships, plumb soundings of ships traversing to and from New Zealand. Fast forward to the early part of the 20th century, and this is a map in a paper by Patrick Marshall in 1910, and you can start to see some ridges and plateaus and a bit more shape emerging from rather than the amorphous isobaths. Interestingly, Macquarie Island is still apparently connected to the Campbell Plateau here, And Marshall and his contemporaries were already talking about a feature called the New Zealand Plateau, which started to describe a wide continent, a wide shelf, shallow shelf around New Zealand. These little clippings up here show that, yeah, at the time people were talking about New Zealand as being continental or part of a continent, but my reading is that these descriptions never got a huge amount of traction in the literature at the time. Nonetheless, geologists were talking about New Zealand as a continent in some way. And then New Zealand Oceanographic Institute, with its dedicated surveys along with many more ship tracks, would produce this kind of map at this scale with the same colour ramp. And yeah, a lot of the undersea features are named, just as the major mountains and valleys of the land are named, so the major rises and platforms and troughs, they've all got names down there. And certainly from these decades here, people were talking about the New Zealand region as a collection of continental fragments, slices, ribbons. This adjective pops up many times in the literature. So already people are twigging to what's out there, but still no coherent continent. Now, the current view we have of ocean bathymetry is something like this. And this has been a real inspiration to a whole generation of geoscientists in the last couple of decades. These are maps derived not from ship tracks and interpolation, but from microgravity measurements made by satellites, made by multiple passes. So the differential pull of gravity allows, if you process that data, you can get a water depth map out of it. And so literally no seamount can hide anymore. Formerly, it used to be that, if a ship hadn't gone over a small seamount, it wouldn't appear on a map. But you can see the fantastic detail that we have now all around the planet, actually, but especially in the Southwest Pacific. It's certainly unlocked and revealed a lot of features, and it's a really good roadmap for marine expeditions to explore and investigate certain features. And you can zoom into this, and in future decades, as there are more orbits made, the resolution will increase and improve as well. So we can look forward to more insights from this data set. Okay, so with this simple bathymetric map, if you were to ask 9 out of 10 geologists in the audience, draw the major geological feature on that bathymetric map, then they'd draw a black line like this. And arguably that's a pretty good line to draw. It's the Australian Pacific plate boundary. I mean, we live in the era of plate tectonics, and it's a major feature in New Zealand with all the earthquakes. It creates the volcanoes in these chains just above the subducting plate. So yeah, arguably that is certainly one of the most important geological lines to draw on that map there. But I would say, at least for the purpose of tonight's talk, that that one is equally important. This is the difference between Zealandia, the continent, or continental crust, and the surrounding oceanic crust. That's another sort of first-order geological feature. So this is going to be what we're going to be focusing on and running down that checklist there. Does it only have enough of these features to be called a continent, rather than just a collection of continental fragments inside that red line? Okay, so the first one then, is it high enough? All right, is it high enough? Well, I've blown up the elevation scale here so you can see. You can see the red dashed line that I've picked out here as being the limits of Zealandia. Coincides quite nicely with this, I think, optimally chosen colour ramp. All right, that's why I chose this particular image between the orange and the blue. So almost everywhere around Zealandia, it's about between 2,000 and 3,000 metres water depth is where we draw the edge of Zealandia. And that's clearly much higher than the surrounding ocean crust, which is down at 4,000 to 7,000 metres. The highest point of Zealandia is Aoraki Mount Cook, 3,724 metres. And that's pretty respectable for any continent, actually. We're pretty proud to have a mountain that high. It's higher than anything in Australia. But you can see, if you look at everywhere within that red line, there's really not much to go on. There's only 6% of Zealandia is actually high enough to poke up above sea level. Obviously, the main islands of New Zealand, the South Island, North Island, Waiheke Island, and and various other islands, Stewart Island. We've got the Subantarctics down here. We mustn't forget Guantere in New Caledonia. That's another very important outpost of on-land northern Zealandia that geologists can put their hammers on and sample and study. And there's various small reefs and islands scattered around as well. So, yeah, I would say we can put the green tick by high elevation. It is mainly below sea level, but it's certainly much higher than the surrounding ocean crust. And I'll get back to this point about why is Zealandia so submerged. How did that come to be? I'll address that later on. Okay, the second point, varied geology. So again, with just 6% exposed to look at in a handy way, we have to scratch around for the offshore undersea part to get samples to check on do we have granites and greywackies and schists and that sort of thing. So we can go to the offshore islands, and here when I talk about basement rocks, I mean the rocks that are deep in the crust that form the foundations and occupy most of the crust of Zealandia, not the thin little sedimentary cover on the top. So there's a few islands, the Chathams and the Subantarctics have basement rocks exposed. Some of the deeper oil exploration wells in Taranaki and Great South Basins go deep enough through the sedimentary rocks to give us samples. There's a few research boreholes, but most of our knowledge of the geology of Greater Zealandia in the offshore region comes from rock dredging. So these are dedicated ship cruisers that go out and throw a steel basket or bag off the back of the ship and literally drag the seafloor at specially chosen points and retrieve rocks. And in 4 slides' time, I'm going to show you a time-lapse movie of some rock dredging going on at this location right here, okay, on this edge of northern Zealandia here. So to go to sea, you need a special tool. You can't just do with a geological hammer and a 4-wheel drive vehicle. You need a tool like this. This is one of a few dozen ocean-going research ships around the planet. New Zealand has the Tangaroa, the Australians have the Investigator, the French, the Germans, the British, the Americans all operate research fleets. I was lucky enough to be on L'Atalante 2 months ago for a 25-day cruise around northern Zealandia, and this shows L'Atalante where we first saw it moored at the harbour in Noumea. And just as you assemble specialist teams to do on-land geology, the same applies offshore. This is the team that went on that cruise, the Vespa cruise. And I've circled the faces of the scientists and technicians. There were 17 of us, 9 men, 8 women from France and New Zealand. Here I am. You recognise Hamish Campbell and Patty Durantz, all from GNS Science. And there's my co-chief, Martin Patriat, from Brest in France. So we're at sea, and the other people there are part of the ship's crew, essential personnel. There were 35 of those, so there's about twice as many support staff as there are for scientists on board. And L'Atalante's an excellent work platform, as every ship I've been on is. And this is the time-lapse movie. So for dredging, imagine that you're up in a balloon, all right, above the surface of the Earth, all right, and you're 3 kilometers high, and you have a basket on the end of a piece of rope that's just 3.5 kilometers long. So you pay out the rope, have a basket on the end, and you drag that basket across some hill or mountain or slope, and you pull it in and see what rocks you've got. You're allowed to look down. You can see the topography. We make bathymetric maps of the ocean. You've got that road map to look at. But you can't, that's the only way you can touch the rocks and get the rocks is to throw a basket over and bring them up. So this is where we join this little clip here. The dredge has been over the side for the last 3 hours. It's taken an hour to pay out down to get to the bottom. It's been along the bottom for an hour, and it's just come up. And it's come up on this main cable here, and the deck hands are about to transfer it to this winch here to bring the rocks on the deck. There it comes up. This is sped up about 10 times. So 20 minutes work condensed to 2 minutes for you here. So they're just transferring it. So is it full? Is it empty? Is the dredge still there? Is it broken off? Here we go. It's been 3 hours, been waiting to see what's gone in there. There's the top of it, and that's pretty good. It's half full, which is good stuff, okay? So all of us geologists are behind this chain here. We're behind the camera, itching to get forward, but before we can do that, the deckhands have got to tip the rocks out, make sure they get every last rock out, because we don't want to contaminate it for the next dredge. There we go. And they'll secure the dredge. They're not getting seasick yet? Okay, they'll tie it down. In a minute you'll see us geos come out. Finally. Get our hands on things. There we go. Okay, so now the ship's going to turn around and head off to the next dredge site. It's a 24/7 operation, always something going on a ship. And you see plenty of sledgehammer action, beating away, smashing these big boulders open. We've got those grey boxes out to put the interesting rocks in. We want to go through that big pile. Is it all the same rock? Are they different rocks? We don't want to miss anything that's different or interesting. We've got to get a representative lot of rocks in that box there. More bashing away. There we go. Back to the lab, and you'll see people start to toss rocks off the back of the ship. Well, they're allowed to do that because it's just impossible to keep all that rock, to archive it. We send archive samples to Noumea. We keep... Nearly done. There we go. Okay. So, overall, on average, we keep about 10% of what comes on board. If there's only a few rocks in the bag, which sometimes there are, sometimes there's nothing, just like being down there and being pulled and dragged. If there's only a few rocks, we keep them all. If there's something like that, yeah, we can afford to be selective and just choose the freshest bits. So this is that same dredge, just when it's first dumped on the deck. When we first go out, there's a label. We take a deck photo of everything. You can see they're not giving much away there, just sitting on there. They're pretty wet, slimy, covered in black manganese. We had a rock saw on board, so we'll, in those grey boxes, take them back, run them to the rock saw, figure out how many different rocks we've got, and we can start to sort them out into different categories and piles on the bench there. And labels, and this is what came out of Dredge 40, that exact dredge. There are basically, well, there are half a dozen different kinds of rock. I've chosen the more photogenic ones here. On the left, 2 different kinds of lava, one with lots of crystals in, porphyritic lava, and one with vesicular lava with holes in, okay? We've got a volcanic breccia here, some multicoloured breccia conglomerate, and here's a mudstone, which will almost certainly give us good microfossils that we can date. And there's probably some datable minerals in this lava as well. So, yeah, the age of these things is all important. So that's just a small aside, if you like, or a taste of how we can learn about, how we can discover about the geology of that 94% of Zealandia that is out there. So that was that dredge there, and there was nothing overtly continental in the dredge that we saw, not in that one, but you can see overall, I've coloured in these same dots now according to rock type, and these are the sort of rocks you'd expect in continents, not in the oceanic realm, and you can see there's plenty of them. It'd be nice to have some more samples around northern Zealandia, but where they're of sufficient density, we can start, and the rocks are the same age, we can start to join them up in these belts or lines, okay? So the schist on the Chatham Islands, and that schist there, and that schist there, and the Otago schist, we think we can draw a line between them all. It's the same belt of schist. And likewise, this belt of granites here that go from the Bounty and Antipodes Islands through Great South Basin, Fiordland, under Taranaki Basin, a couple of dredges here. Yeah, there's geological reasons to continue this geology through Zealandia and into Australia in one direction, into Antarctica in the other direction before it broke up. So there we are. I think we can, hopefully I convince you, we can put a tick by the varied geology. Right. And to me, the varied geology is one of the most important criteria of the continent. But some people might say, well, okay, but it could be that you're just lucky when you get these little bits of continental rocks poking up. How do you know that there's continuous thick crust between them? Okay, they could just be random. They could still be continental ribbons and slices just being poked up through the ocean. Well, this is where the geophysicists come in again, and this is another microgravity map. more of the raw data rather than processed for bathymetry. So the colours are different levels of gravity, but the black contours are the thickness of the crust in kilometres, okay, that's derived from modelling of that gravity. So Australia has a typical continental crust thickness. It's always more than 25 kilometres, sometimes gets up to 40, okay? That's pretty typical for most normal continents. You can see Zealandia. The only place Zealandia is greater than 25 k's is in the central part under the two islands. And that kind of makes sense because it's thick and buoyant and pokes Mount Cook up to the top. But even so, the rest of Zealandia, the Campbell Plateau, Chatham Rise, Lord Howe Rise, we're always more than 15 kilometres. And everywhere we're greater than 10 kilometres, which is the typical, ocean crust is always thinner than 10 kilometres. So even though Zealandia is thinner than a lot of typical continents, we are always thicker than oceanic crust. So I would say we can put a tick by the thick crust item as well for Zealandia. What about the area? Okay, the continents do have to be big. Is Zealandia big enough? So I'll spend a couple of minutes on this slide here. The x-axis is area. It's a logarithmic scale. So this shows the area of various superficial features. The biggest continent is Eurasia. That's why it's there at the right-hand end. There's Zealandia, 4.9 million square kilometres. And these things down here are various other features that lurk out in the oceans. Fiji, Mascarene Plateau has been called a microcontinent. Ontong Java Plateau is a big basalt plateau in the Pacific Ocean. And I've shown how other features like India is smaller than Zealandia. Greenland and Madagascar, sort of islands that belong to big continents here. Now the y-axis is the area of each of these things below sea level. So the most buoyant continent, the continent with the narrowest continental shelves and the most land, is Africa. Okay? And the most submerged continent on planet Earth, with 94% submerged, is Zealandia, down at the bottom. But it's interesting that you can see if you divide Antarctica into two halves, East Antarctica and West Antarctica, then most of West Antarctica, if you take away the ice sheet and allow things to re-equilibrate, then most of West Antarctica would be below sea level. In fact, it would be quite close, it would be about 90% submerged. So Zealandia is not unique or not on its own in being a large continental mass that's so submerged. And later on I'll show you a slide that explains why Zealandia and West Antarctica might be in this special case here. We do understand, at least broadly, why that should be. But as far as the x-axis goes, large area, I think there's a case to be made that, Zealandia, although it's the smallest continent, it does naturally belong with this group here, rather than with these things that have been branded microcontinents and oceanic plateau. Okay, what about the limits? Okay, we have to be able to draw a line around it, okay? Or is Zealandia so close to Australia that Australia should actually be part of Zealandia? Yeah? How does that stack up? Well, you can see from most of the perimeter of Zealandia, it quite happily abuts oceanic crust. Notice there's the Kermadec Ridge, the Colville Ridge, and down here the Macquarie Ridge. These are not part of Zealandia. These are ridges, they're buoyant, but there's no granites and gneisses or continental crust along there. These are just caused by volcanoes related to subduction. So we don't include those, but we'll zoom into that region where Zealandia comes against Australia. Okay, and this is what we have. These are two maps that are at the same scale. There's a 200-kilometre scale bar there, okay? So the closest approach of Australian and Zealandian continental crust is 25 kilometres. That's all the separation that there is. This is across a feature called the Cato Trough. And you might think, well, that's not very much, is it? But if you actually look at the boundary between Africa and Eurasia today, it's along the middle of the Red Sea. There's a mid-ocean ridge spreading axis there. And at its widest, the ocean crust strip in the Red Sea is only 40 kilometres wide. Okay, this is the continent-ocean boundary here. And even through the Gulf of Aden, it actually narrows to zero. There is no oceanic spreading. So there's that to think about. even though there's only 25K separation, there's actually been, this gap here is controlled by a feature called the Cato fracture zone. And this is a strike-slip fault or a side-to-side fault. It's actually had 150 kilometers of displacement on it. So this corner of Zealandia here used to slot into this little elbow of Australia here, okay? And so the separation has moved them apart by 150 kilometers. So again, although admittedly, there's only a narrow separation, the closest approach, there's actually been 150 kilometers of tectonic separation, which is pretty respectable, much more so than between Eurasia and Africa. So I would, again, put a tick by this aspect as well. And the last one is old bits of crust. And by old, geologists mean something that's Precambrian, so it's older than 540 million years. The Earth itself is 4,600 million years old. And how does New Zealand stack up there? Well, many of you may know about the oldest fossils in New Zealand. They're trilobites, trilobite rock in the Cobb Valley. There's trilobite rock there. So these are 505 million years old. They're actually beaten for the oldest rocks in New Zealand by some rocks nearby in what's called the Cobb Igneous Complex, and zircons have been dated at 10 million years older than that. But we're still in the Cambrian, we're not in the Precambrian. The oldest dated object in New Zealand, and therefore Zealandia, is actually a grain of zircon. That's that brown, unremarkable brown grain in the center of the field of view there. That's a 1 millimeter field of view. So this zircon grain, a zirconian silicate, is 100 microns long. And my colleague Chris Adams has dated it as 3.5 billion years old. Okay, so 3,546 plus or minus a bit million years old is that sand grain of zircon that he found, well, extracted from a Greywicky sandstone. So it's not a rock that you can say formed in the Precambrian. It's only a sand grain that made its way into a rock that formed 450 million years ago. The grain itself was probably formed in Gondwana or Australia or Pangaea and found its way in there. So we have some sort of deep earth antiquity here, but nothing in the crust, but nothing that's really Precambrian like other continents have. But one thing we do have, and this is quite recent science, this, and we're still puzzling as to why that should be. So I've been talking about the crust so far, but the mantle underneath New Zealand, so the green mantle down here, we can actually get samples of the mantle, remarkably. And we sample the mantle when lavas erupt, and they rip up bits of the mantle and bring them with them as small chunks, or xenoliths, as they're called. So this peridotite nodule here came from the mantle underneath here. And these days, it is possible to do dating work on peridotites. For a long time, it wasn't. But you use the isotopes of the elements rhenium and osmium. And James Scott and Alex McCoy West have done this in a few volcanoes. Not every volcano gives you bits of mantle material, but some do. And you can see these are the dates they get. Some remarkably as old as 2.7 gigayears. So, yeah, even if the crust of New Zealand isn't really old, a lot of the mantle down there is. And, yeah, it's an ongoing topic as to how the two relate to each other. But I just thought I'd throw this slide in as, you know, we do have sort of old objects. So I would say that the yeah, by and large, so I've put a tick by all of these bullet points here. Zealandia is high. It's got the varied geology, thick crust. It's big enough. It's surrounded by ocean crust, and parts of the crust are at least getting pretty respectable. So you could say, if you want to use some superlatives, that Zealandia is the Earth's most submerged, thinnest, smallest, and youngest continent. Okay. And I'll put the arrow there because each of those statements is actually worthy of a lot of scientific study in itself to answer the question how or why did Zealandia come to be like that. It's an end member of a spectrum of continental properties. So yeah, that alone I think is worth putting Zealandia on the Earth's continental map. So we should be able to get some insights into the processes of continental formation and breakup if we investigate these things. All right, we'll change gears here and just talk about names for a bit, about the name New Zealand and Zealandia. And, okay, so Tasman was the first European to come here, and he called New Zealand Startenland. Okay, he didn't call it New Zealand. He called it Startenland, which is the then name of the Netherlands, because he thought that it might be conjoined with another Startenland that another Dutch explorer had discovered in the southern tip of South America. He thought that maybe this is part of the southern continent. Okay, so that's why he called New Zealand Startenland. However, in 1644, there was another Dutch expedition to southern South America in which the explorer, whose name I've forgotten, actually did a lot more circumnavigation and determined that no, that was not the case. The Startenland in Terra del Fuego was actually an island. It didn't extend westward across the Pacific. So from the mid-1640s, the Dutch cartographers and explorers understood that New Zealand was not part of Startenland. And so it was as early as 1648 that the Dutch cartographer Johan Blauw was putting New Zealand on the maps. So Startenland was only a very, very transient and temporary appellation for us. Where did the name Zealand come from? Well, there is a province in the Netherlands called Zealand. It literally means sea land, and there's a lot of islands down there. It's frequently flooded. I've not been able to determine a direct connection between that. Obviously, Sealand is an appropriate name for some islands in the Pacific. But one thing that is very appropriate is the emblem and the motto for the province of Zealand in the Netherlands. I struggle and I emerge. So what better motto is there for a 94% submerged continent, eh? And likewise, that a very striking emblem there. So that's good. So what about Zealandia? Well, there she is. Meet Zealandia, everybody. Here she is in all her colonial glory. You can still see Zealandia as one of the two people on the New Zealand coat of arms. She's appeared on stamps, on coins, given a name to many, many ships down the decades. And most recently, of course, the eco-sanctuary in Wellington. If you go to Google and bang in Zealandia, you'll bring up lots of pages about the Wellington eco-sanctuary rather than the continent. And if you want to see Zealandia, there's 3 places in New Zealand you can go to see her and touch her. There are 2 marble statues in Palmerston and Waimate in the South Island. And there's a plaster of Paris copy in the Auckland War Memorial Museum. So these are the only 3 I know about. There may be others around, but these are all Boer War memorials, okay, again reflecting the colonial New Zealand symbolism, okay. But the first use of the term Zealandia in the geological context was not by anyone at GNS or anyone in New Zealand. We owe that to this American geophysicist, Bruce Lyondike. And he wrote a paper in 1995 in the journal Geology, in which, and I've underlined it, he refers to Zealandia as a collective noun for New Zealand, the Chatham Rise, Campbell Plateau, and Lord Howe Rise. And figure 1 in his paper, which I've colorized up here, shows a thinned continental crust Zealandia between the Pacific Plate and West Antarctica. So, I mean, Bruce deserves credit for this. He's the first person to use the term. But Bruce, in the paper, Bruce did not develop the concept or define it at all in anything like the way I've defined tonight. All that work has come since. But precedent being what it is in science, yeah, Bruce deserves the credit for it. And it was a good name. It rolls off the tongue easily. And yeah, that's why we're running with it and promoting it. So by the same token, prior to 1995, nowhere in the geological literature will you see the word Zealandia used. Okay, it is a fairly recent construct. And we can understand where the next few slides are about Zealandia's origins, where it came from, and how it slots into Gondwana, and how it sits shoulder to shoulder with other continents. When I bought this jigsaw puzzle about 25 years ago, it was a 5-piece jigsaw puzzle. Right? New Zealand was part of the Australian piece. But before we wrote the book here, I thought, well, this won't do. So I took a saw to the Australian piece and revarnished and relabeled it, and so we actually have a 6-piece jigsaw puzzle for Gondwana. So that's how Zealandia fits into Gondwana there. And you can see the family tree there, Zealandia with part of the present-day continents, and if you go back in time, back to the parents and grandparents, we can see that Zealandia was an integral part of Gondwana, Pangaea, and so on. And how it came to be? Well, it's quite a journey, of course. Today, in the top left is where we are, between 30 to 60 degrees latitude. That irregularly shaped pink object. It's been quite a journey. 110 million years ago, Zealandia was a very thin ribbon plastered along the side of Gondwana, as was West Antarctica down here. Okay? And you'll notice one of the interesting things is between this time, 110 million years ago, and this time, 85 million years ago, Zealandia has doubled in area about, okay? Its volume has remained the same, so it's doubled in area and it's thinned by half in round numbers, okay? And that geological event there, the thinning and stretching of Zealandia, more or less condemned it to inevitable sinking and submergence. And the same applies to West Antarctica. And this, in very simple terms, is how we understand why New Zealand is submerged like it is. 100 million years ago, the long-lived subduction had just stopped. We had a mountain range called the Cordillera Zealandia, a nice, thick, chunky crust, conjoined, everything was Gondwana here. Fast forward 20 million years, and this stretching has gone on, so the surface area of Zealandia is much bigger than what it was, about twice as big, but the volume stayed the same, so it's thinned, okay? It's a process called rifting, geologically. It was still part of Gondwana, and then eventually the stretching proceeds to the point where eventually it breaks and snaps instead of stretching like toffee, and the Tasman Sea forms, and that's the point. The seafloor formation of ocean crust here is the birth of Zealandia, and it moves away to the north. So it's just thinning process because given time, thin crust will cool and it'll sink, float lower in the mantle than a buoyant continent, a buoyant thick continent. A thin continent will sink lower than a thick continent. So I've got a little movie here of that to show you, the second movie of the night. There's a few of these around, little plate tectonic movies. You can see continents breaking up and doing things. This one's special. This was made by my colleague Simon Williams at the University of Sydney. It used some software called G-plates. It's very nice Australia, Antarctic, Zealandia centric. So instead of being jammed in the bottom corner of a globe, we're front and center. Instead of just using rigid plate tectonics, which a lot of the earlier models use, Simon has here incorporated this stretching of Zealandia and parts of Australia before the formation of ocean crust. So the first few frames, between 100 million years and 80 million years, you'll see this red region expanding and stretching, and then it'll break off and the pale blue will carry on, and you'll see Zealandia moving north. So I'll play this a couple of times, but you see what I mean. So we're stretching, all those red little movements in the triangles are the stretching where he's got non-rigid continental crust. We're going north there, and then pretty soon Australia begins a really rapid journey. And there we go. So bear in mind, this is only a model, it's not reality, okay? So we've got to 0 million years, he's not shown the Pacific Australia plate boundary, that big line there. You've seen some New Zealand coastlines crossing each other. That's not being modelled either. That's simplified out. But basically what this shows is these areas of West Antarctica and Zealandia that are stretched out, which no other model previously has shown. So that's an advance. There we go, one more time. So don't worry about the overlap between the North Islands and the South Islands there. That's not part of this. But this, you might think words like plastic, shouldn't apply to rocks, but on these sort of time scales, that they do. That's how they behave. Okay, so Zealandia. Is Zealandia in the same category as Atlantis? How fringe is this? Okay, has there been a scientific uptake? Is it a respectable continent, or is it one of these kind of mythical things that maybe, maybe not? Well, it's been quite gratifying in the last 10 years. I think we at GNS and in New Zealand are not the only ones using the word Zealandia, as Bruce Lyndike intended, but yeah, an increasing number of overseas researchers, Australians, Americans, Germans, are using it. This is just a selection of paper titles, scientific paper titles, in which the word Zealandia occurs. So it's been a soft sell so far. There's been no blockbuster paper in Nature or Science, about Zealandia, but we're kind of, growing it slowly. So I'll finish off with a few pictures of, the Zealandia in 2015. You remember the earlier picture I showed of colonial Zealandia? Well, I was delighted to discover this piece of street art in Ponsonby, which shows a much more, a Pacifica, much more contemporary Zealandia. And of course, Zealandia is a continent that spans 3 countries. Okay, we've got Australian territory, French territory, and New Zealand territory in here. But so it certainly takes in Melanesia, Polynesia. And Auckland, here in Auckland, you're not just New Zealand's largest city, you're Zealandia's largest city. Okay, the largest city of the continent and commercial centre. Talking of territory, I've been talking about, I could have a whole hour's talk on just this one slide, okay? There's too much in here, but tonight I've just talked about the red line, okay, defining the research geological limits of Zealandia continental crust. The New Zealand exclusive economic zone is shown in the black line. That's the 200 nautical mile radius from coastlines. And the recently established New Zealand extended continental shelf is shown in white. And this was a claim put to the United Nations Commission by New Zealand in the last 10 years, and it's been ratified and approved by the UN. And so this defines the seabed over which New Zealand has rights, has territorial rights. You can see this extends beyond the red line always. Where the black line gets cut off is where we butt up against the Australian 200 nautical mile radius, okay, on Norfolk Island up here, and then Macquarie Island down here. So a question I got last night in Hamilton when I gave the talk was, well, surely with Zealandia there we can have a territory grab to the north. We can take some more. It's ours, isn't it? Well, the answer is no, because that white line is all done and dusted, and it's been pre-agreed with the Australians before both countries went to the United Nations for ratification. So the cake's already been carved up. And of course, the fact that there's a scientific continent there is different from there being a political entity. Nonetheless, the EEZ and ECS do focus your mind when it comes to things like natural resources. And every continent comes with its cargo of sedimentary basins, shown in the yellow there. And these are places where you find oil and gas and the like. We can also understand a lot of other of New Zealand's natural resources much better if, in a continental context. If we put Zealandia front and centre, it helps explain why we've got gold and tungsten deposits instead of being stuck out in an ocean somewhere where continents have these metals, enrich these metals. The collisional mountains of the Southern Alps between North Zealandia and Southern Zealandia have given us the mountains that give us the potential energy to make a lot of hydropower from, okay, and rainfall. That only happens in continents as well. Likewise, the geothermal activity we've got, if there wasn't continental crust there, we probably wouldn't have as much of a geothermal resource. And the same would go for things like silica sands that we can make solar panels out of. Silica is an element you find it's concentrated on continents. If you're not a resource person, then, yeah, in terms of conservation ethics and that sort of thing, then, yeah, the New Zealand flora and fauna, we're not just carrying a national cargo, we're carrying a continental cargo with us. And many of you may have heard of Zealandia for the first time in the context of whether Zealandia was totally submerged or not, totally flooded in the Oligocene. My colleague Hamish Campbell made quite a thing of this a few years ago. You can see today New Zealand's 94% submerged. The question is, back in the Oligocene, was it 99 or 99.9 or 100% submerged? either way, whether the flora and fauna have come by repeated colonization from Australia, or maybe some are relict flora and fauna from Gondwana, either way, we've got a continental cargo with us. A very special one. And again, they've been subjected to this reducing land area pressure as they've evolved. And for those of you who like to run marathons on every continent, if you run marathon a year on the world's 7 continents, or climbed the highest peaks on all the 7 continents, well, there's an 8th one you've got to add to your list now. So it's back to square one. There are more marathons to run and more mountains to climb and more activities to do because there's another continent. Okay, so the penultimate slide now. I've pretty much put the case for Zealandia tonight, but of course nothing's ever finished or finalized in science. And sometimes fairly simple things can give you windows and ideas for what's going to come next. So mainly tonight I've been using the GNS rendition of the satellite gravity map shown on the left there. And that's because the colour ramp very nicely thresholds this difference between continent and ocean crust that I wanted to bring out tonight. But we can get an idea for the next step forward from an EWA rendition of the same data set, plus adding in very detailed multi-beam tracks that are increasing in number around New Zealand. And you can get a much higher resolution map. And with something as simple as a different colour ramp and different shading, you can already see more details in that map on the right than you can in the one on the left. Maybe Zealandia isn't just a one-level, Zealandia into ocean crust. You can see the orange to yellow transition suggests that there's maybe a 3-level Zealandia, okay? A low part that may be more stretched. This part here may be less stretched, and then you've got the collisional zone in the middle here. So this also highlights that some edges of Zealandia are very sharp, and other ones are more sloping. So yeah, this inspires all sorts of research directions. So it's a cliche that New Zealand is a natural laboratory, but we can also promote Zealandia as a natural laboratory to study continents. And certainly I think because New Zealand is that extreme, although superlatives I apply to it, certainly there's something to learn about the Earth's continents in general, about processes and rates of stretching from Zealandia. Right, that's almost it, folks. I hope that one day maps like this will become very familiar and used in atlases and on the web and around the place, that gradually the uptake will happen, that people will recognize Zealandia is a continent out there. Hopefully you've enjoyed and been informed by tonight's sort of run through the various criteria for it. And we're going to end with a vote, actually. It'll be a secret ballot. What I've got here are some fridge magnets of Zealandia, okay? And I'm going to pass these around during question time. And if you're convinced that Zealandia is the Earth's 8th continent, please take a fridge magnet. If you're not convinced, then just pass it on. Okay, thank you.